Welcome to next lecture. In this lecture we will study the actual design of modulators. In particular, we will first of all motivate ourselves that the modulation for DSB-SC is attained when we multiply a message signal with the carrier signal. Okay, so we have multiplier-based modulators and also we have switching modulators. Okay, so as you know from the previous lectures that here is the simple goal. You have a message signal and you have a high frequency carrier wave. Okay, you want to multiply them and the result m of t. Okay, so this is your DSB-SC double sideband suppressed carrier signal which you can transmit via antenna. Okay, so one of the ways is that you can directly use multiplier, circuit. Okay, but we will not go into the actual design of multiplier circuit. Nevertheless, it is a transistor based circuit, but there is a non-linearity issue there. Non-linearity means that any, even transistor is a non-linear device, right? So if you use any such circuit, multiplier circuit, okay, so you have here m of t and the other thing you are feeding in is cos omega ct. You will not only get m of t cos omega ct, but you will get terms like m square t cos square omega ct, m cube t cos cube omega ct, and higher orders also. So it becomes very costly, it becomes very difficult to mitigate the effect of non-linearity. These m square, m cube terms, to cancel those terms. So we will not go with that. In fact, let me tell you that if x of t is the input to any non-linear device, okay, even your diode is a non-linear device, right? So it means any diode, transistor. So the main dominant terms will be, so the output will contain a term of xt and x square t. There will be higher orders also, but they will be of less magnitude. So the coefficients a and b will have sufficiently good value. Although there will be c x cube t, but the value of c is very less, so we can neglect this x cube t, higher orders. So the dominant terms in any non-linear device are at least one is a linear term and the other is a non-linear term. Non-linear term. Okay, so there is one way that we can use not just one non-linear device. We will use two non-linear device in little bit intelligent way. So let's see, here is one way. So now I call by NL the non-linear device. NL means non-linear device. Okay, so it can be any diode or it can be a transistor also. It can be any non-linear device. Now if you have here m of t message signal and here is your cos omega ct, okay, and instead of one non-linear device you use two non-linear devices, one here and one here. Now what will we do? We will add m of t and cos omega ct and feed it to one nonlinear device. Okay, and we will subtract minus sign here. We will subtract m of t. We will subtract cos of omega ct from m of t and feed it here. Let's call this x1 of t. Let's call this x2 of t. So x1 of t is m of t cos omega ct. x2 of t is m of t minus cos omega ct. Oh, sorry, we can write cos omega ct minus m of t. Not much difference, but sign will be different. So cos omega ct minus m of t, right? Because we are showing minus sign here, so this is plus times cos omega ct. This is minus minus m of t. So that is what it becomes here. Now let's call this as y1 of t and this as y2 of t, and again let me subtract y2 of t from y1 of t. We will get z of t. Now let's analyze what all this is. Very simple. It's not so complicated. So we know that the input output relationship of a nonlinear device is y of t is equal to ax of t plus bx square t. So accordingly y1 of t will be equal to ax1 of t plus b x1 square t, and y2 of t is ax2 of t plus b x2 square t. Okay. Now what is x1 x2? So x1 of t is cos omega ct plus m of t, and x2 of t is cos omega ct minus m of t, right? So no issues till now. Now the output here is z of t as the design is there, so it is equal to y1 of t minus y2 of t, which is ax1 of t plus bx1 square t minus ax2 of t plus bx2 square t. So far so good. Now we will substitute x1 x2 as they are defined in terms of carrier wave and message signal. So here is this a x1 of t is cos omega ct plus m of t plus b cos omega ct plus m of t square minus a cos omega ct minus m of t. See, it is now x2 here, okay, plus b cos omega ct minus m of t now square. So in x1 of t it is cos plus m of t, in x2 of t it is cos minus m of t. Okay, so we see some cancellation right here. So at least a cos omega ct that gets cancelled. Okay, now here is a times m of t, here is a times minus of minus is plus, so it is 2a m of t. That is one term, plus b is the common term, then it is a square here, okay, square here and square here, so it is cos square omega ct plus m square t plus 2m of t cos omega ct, that is 1, minus cos square omega ct plus m square t minus 2m of t cos omega ct. So cos square and cos square gets cancelled, m square t gets cancelled, 2m of t cos plus 2m of t becomes 4m of t cos omega ct. So it becomes 2 times a m of t plus 4 times, I think it is b, m of t cos omega ct. Now out of these two terms, okay, which one term is double sideband modulated signal suppressed carrier? Second one, right? So in fact 4b is simply a constant. If you look at this m of t and cos omega ct, so this is the desired DSB-SC signal, right? Okay, and this is unwanted part. Now how to get rid of m of t? Let's go to the frequency domain. So if you see, m of t is a message signal, and if its Fourier transform is suppose m of omega, since it is message signal, it can be voice signal, it can be video, it will be of low frequency, okay, also called baseband. It's also called a baseband signal. Okay, so m of t will be somewhat like here, m of omega. Now you look at this second term, m of t cos omega ct, its Fourier transform is m of omega plus omega c plus m of omega minus omega c. There will be some constant here, 4b, but omega c is quite high, so its spectrum will be somewhat here, right? Now how to get rid of this? See, what should we use? So any guess you can make? We should use band pass filter. If we use band pass filter, which will only allow these two, this is the band pass filter actually, it will only allow these two, that is the spectrum corresponding to m of omega plus omega c and m of omega minus omega c. It will exclude this spectrum m of omega. So it means that z of t, which is equal to 2a m of t plus 4b m of t cos omega ct, when that is passed through band pass filter, of course centered around plus minus omega c, right? Omega c के center के around होना चाहिए. Then you will get 4b m of t cos omega ct, right? Then you can put simply an amplifier of gain 1 by 4b. You will get m of t cos omega ct. Nice. So if we go back to the diagram here, so what should you place here at the output of z of t? Band pass filter centered around omega c, and that will give you 4b m of t cos omega ct. Okay. Sorry. Now this is one way to realize the DSB-SC modulator, but even there are other better ways. So one of the famous way to design it, and I think most commonly use it, those are called switching modulators. See, one thing you should bear in mind. What is our target when we talk about DSB-SC modulators? Remember, the target is to get m of t multiplied with cos omega ct. That is it. Okay. Now today I will just briefly tell you about what switching modulator means. Sorry. See, switching modulator means, suppose you have a message signal, okay, and you apply it to some circuit, okay, we call this as switching circuit. Switching circuit means that it will generate, some on-off signal like this. Okay, so this circuit is getting on and off according to the message signal. Okay, now if you look at this on-off signal, okay, you forget everything right now. Just look at this periodic signal. Okay, it can be of this type, it can be of this type, which never goes negative. Okay, so there are several types of such periodic signals. Now one thing is there, how can you represent such a periodic signal? You know that Fourier series is used to represent periodic signals, right? And any circuit which generates switching such signals, periodic signals, and you multiply m of t with that, now what will happen? So first of all, you represent the Fourier series representation of this signal. Okay, so a general way of writing Fourier series is phi of t, suppose, is equal to some coefficient Cn cos of n omega ct plus phi n theta n. See, you might have seen a Fourier representation like this, an cos of n omega ct plus summation of bn sine of n omega ct. Okay, so that is one way. This is another way to write Fourier series. So what is the logic for, so this one you might be knowing, you must have done it. So now what can we do is, if we take an cos n omega ct plus bn sine n omega ct, with simple trigonometric transformations, you can write this whole thing as some Cn cos of n omega ct plus theta n. You know that how to do it, right? So you do that like this. So you write it as r. So in fact you write an, let an be equal to some maybe, so Cn cos theta n, and bn is equal to Cn sine theta n, right? You write a and bn in this way, and then you get Cn is equal to under root of an square plus bn square, and theta n is equal to tan inverse of bn by an, right? And when you substitute an and bn in this way, you directly get their Cn cos of n omega ct plus theta n. Okay, so they are equivalent ways of writing the Fourier series. So for us, this form is most convenient, and it goes directly as the result. Now any periodic signal can be written in Fourier series like this. In particular, if periodic signal is of this type, on off signal, so that also can be represented in terms of Fourier series, but the values of Cn theta n will be different. Okay, now if you multiply now m of t phi of t, what will you get? So you will get Cn m of t cos of n omega ct plus theta n, right? Now if you give the values of n, so you will get the first term as Cn m of t cos of, the first term will be the constant cos of theta n plus theta 1 in fact. The second term will be C1, so this is C0 m of t cos of omega ct plus theta 1, plus then there will be other terms, n is equal to infinity Cn m of t cos of n omega ct plus theta n. Okay, now if you see again the second term, this is the desired signal, desired term, and all other terms are unwanted terms, this and the other terms, right? And again, if you put a band pass filter around omega c, that will only allow this term. See, in Fourier series, now if you look at the Fourier transforms of this, so one is the m of t which sits here, m of omega, then there is m of omega plus omega c here, and its second part m of omega minus omega c here. Then there are higher harmonics, right? At 2 omega c, at minus 2 omega c, then at 3 omega c, at minus 3 omega c. But what you will put is, you will put a band pass filter around this, okay, band pass filter. So all other terms, all other harmonics will be that will be cancelled up. So it will not allow this, it will not allow this, it will not allow these terms, sorry, so it will only allow this one. Okay, so maybe this may not be like okay for all of you, so don't worry, because in next lecture we will particularly do a diode based switching modulators, wherein we will again revisit, so we will be doing a modulator wherein the switching signal is like this. Okay, we will use it as Fourier series form, and then we will see how we get the DSB-SC modulated signal. The other switching signal that will be used is this one. Okay, so since this switching signal, it returns to 0, it is sometimes called return to 0 signal. And this switching signal, it never comes to 0, it becomes either plus 1 or minus 1. It's called a non-return to 0. Okay, so in next video lecture we will study in detail again the switching modulator with particular very simple structure of the circuit. Okay, you will see that in fact the diode rectifier which I have done, which I have studied, that itself can generate such signals. That we will see in next lecture. Okay, thanks for watching.